Eigenvalues in exterior domains. Then I will discuss the Robin Laplacian in the exterior domain of the hyperbolic plane. And finally, I will present our new findings. And in the third part of my talk, I will discuss our new results in hyperbolic setting. So first, I would like to be mostly Euclidean in the beginning of my talk, and I will overview some results in exterior domains in Euclidean case. So omega is the setting in the Euclidean space is the following. Omega is a bounded simply connected planar domain with C-infinity smooth boundary for simplicity, and by nu I denote outer unit normal vector to the boundary. The exterior domain is the complement of domain omega in the plane. It's unbounded domain with compact boundary, and alpha is a real boundary parameter. So we looked at operator which is Robin Laplacian on omega exterior. It acts as minus Laplacian on functions in the Sobolev space H1 whose Laplacian is in L2 and which satisfy the Robin boundary conditions. Here the normal derivative is counted with minus because the outer unit normal vector for omega is in a normal vector for omega exterior. And this operator is self-adjoint and semi-bounded in L2 on omega exterior. And the essential spectrum of this operator is positive semi-axis, and the discrete spectrum is non-empty if and only if the boundary parameter is negative. So if boundary parameter is negative, we have some negative discrete eigenvalues, and it's interesting to optimize them with respect to shape of omega. So now we assume always that boundary parameter is negative, and by lambda 1 alpha omega x I denote the lowest eigenvalue of this operator, and by d I denote a disk. So what we proved with David in 2020 that if you fix either the area of your domain, so you say that the area is the same as area of the disk, or you say that the perimeter is the same as the perimeter of the disk, then the lowest Robin eigenvalue on the exterior of omega doesn't exceed the same eigenvalue for the exterior of the disk. And we also considered, we worked on that even before. We had a paper before that, but it was only for convex domains. And we have also addressed more involved cases when omega consists of several connected components. Still, the exterior problem becomes interesting in this case. And a different point of view that exterior domains, although it's a new setting, it is not completely new because it can be viewed as extremal case of doubly connected domains. And in doubly connected domains, optimization was studied before by Hersch and Payne-Weinberger and others. And here, this domain, exterior domain, it can be viewed as doubly connected domain when you send boundary to infinity. So for higher dimensional case and the second eigenvalue, there are also some results which I will briefly mention in my talk. So first, in higher dimensions, in dimensions 3 and higher, the exterior of the ball is not a global maximizer of the lowest Robin eigenvalue, neither under fixed volume nor under fixed perimeter. What we could do with David, that we proved that exterior of the ball is a maximizer of the lowest Robin eigenvalue among exteriors of convex domains if we fix the averaged d minus first power of mean curvature. And more recently, Lukas Bandrok, he wrote a PhD thesis on exterior problems. He proved that even though the exterior of the ball is not a global maximizer, it is still a local maximizer under fixed volume constraint. Somehow I need to point it here. So the second Robin.
Is it the same as fixing the diameter?
You mean fixing this number?
Yeah. If you have this.
This I don't know, but if you know, if you can argue that. I think it's not the same, but I have not seen so.
Topics inequality which bounds the diameter by exactly this something like this. That doesn't matter.
We can talk about it. Yes. We came to this constraint by trying to find a good quantity that gives result. And for the second Robin eigenvalue on exterior domains of you can still optimize. You can still look at high eigenvalues because at this problem you can have several eigenvalues below the bottom of the essential spectrum. And the second eigenvalue, we proved that it's maximized by exterior of the disk. Among exteriors, all planar convex. We had convexity at assumption, and we assumed that the elastic energy of the boundary is fixed, the integral of the square of the curvature. And we conjecture that the same optimization result holds if you fix perimeter or area of the domain even without convexity assumption. And this will be the last overview slide. So there was some work by Lukas Bundrok, Georgi, and Smits on optimization of eigenvalues of Robin P. Laplacian on exterior domains, and they found analog of what we did with David for Robin P. Laplacian. And then there was a very recent work by Lukas Bundrok, Alexander Giroir, Denis Gribenkov, Michael Levitin, and Iosif Polterovich on Steklov problem on exterior domains. And this was a complete retest of this Steklov problem with various results. But let me mention one of them. They proved an analog of Weinstock inequality on exterior domains, that the first non-trivial Steklov eigenvalue is maximized by exterior of the disk among exteriors of Lipschitz simply connected domains of fixed perimeter. And this result is very much related to the second Robin eigenvalue that we worked on. And this year we also worked with Ayman Kashmar on optimization for magnetic Steklov problem in exterior domains, and we could also prove optimality of the exterior of the disk for the lowest magnetic Steklov eigenvalue. In the magnetic case, even the lowest Steklov eigenvalue is not zero and depends on the shape of the domain, and we worked also on that. And all these results were in the Euclidean case, and then we asked ourselves if we can go to manifolds, and most natural manifolds are with constant Gaussian curvature. But if you are on a sphere, you cannot distinguish between exterior domains and bounded domains, so we naturally came to the problem in the hyperbolic plane that was interesting to us. And maybe I don't have to say what is hyperbolic plane here, but so just a few words. The hyperbolic plane is unique, simply connected two-dimensional complete Riemannian manifold with constant negative Gaussian curvature equal to -1. And you can introduce Lorentz inner product, which is similar to usual Euclidean inner product, but the first component are counted with minus. And this is a product in three-dimensional Euclidean space. And then the hyperbolic plane in this model can be viewed as all vectors in R3 whose Lorentz inner product with itself is equal to -1, and you should fix the branch that the first coordinate is positive, and there is natural Riemannian metric on this manifold, which is defined by the restriction of this Lorentz inner product to the tangent spaces. So the hyperbolic distance in this hyperboloid model of the hyperbolic plane can be expressed this distance between 2 points as hyperbolic arccosinus of minus the Lorentz inner product of the points in the hyperbolic plane. And what we also used in our analysis is geodesic polar coordinates. So if you fix some point in the hyperbolic plane as the origin, so in geodesic polar coordinates we can parameterize any point as hyperbolic functions of the distance to this origin and some parameter theta which runs from 0 to 2 pi. So these coordinates we also use in our analysis of the model. And the metric in these coordinates requires such convenient form, and the Laplace Beltrami operator looks as follows, where it is in these geodesic polar coordinates you have compared to Euclidean case you have hyperbolic functions of radial variable instead of usual case. And the operator we looked at is the Robin Laplacian on exterior domain in the hyperbolic plane. So now we, in the rest of my talk, everything will be in the hyperbolic plane. So omega is a bounded, simply connected Lipschitz domain in the hyperbolic plane, and exterior domain omega x is the complement of omega in the hyperbolic plane. I also use notation mu for Riemannian measure on the hyperbolic plane and notation sigma for one-dimensional Hausdorff measure on the boundary. And again, I have boundary parameter alpha, which is real. And the operator I'm going to study is introduced via quadratic form, which is defined on all h1 functions on the exterior of omega, and it is the form is given by squared L2 norm of the gradient of the function plus alpha times squared L2 norm of the trace of the function on the boundary. And this form defines self-adjoint Robin Laplacian on the exterior of omega, and this is the operator we are going to study. So the essential spectrum of this operator is from 1 over 4 till infinity. It is the same essential spectrum as for the free Laplacian in the hyperbolic plane. And the lowest, we are interested in the lowest spectral point of this operator, which we define as the infimum of all h1 functions on the exterior of omega of the expected Rayleigh quotient. And if you take any trial function with non-trivial trace on the boundary, you see that this lowest spectral point tends to minus infinity as alpha tends to minus infinity. So if alpha is negative with sufficiently large absolute value, the lowest spectral point is below the bottom of the essential spectrum, and it is thus a discrete eigenvalue of your operator. So then it makes a reasonable problem to look at how this eigenvalue depends on the shape of our domain. In this exterior problem, there is some natural quantity which is critical boundary parameter. So if you look at your lowest eigenvalue as a function of your lowest spectral point as a function of your boundary parameter, then this function is non-decreasing, and thus you naturally want to introduce the supremum of all boundary parameters such that the lowest spectral point is indeed a discrete eigenvalue, that it is below the bottom of the essential spectrum. What we checked with Antonio and David, that this critical boundary parameter is non-positive if omega is C2 smooth and convex, and it is even negative if omega is C2 smooth and strictly convex. So in comparison with the Euclidean case, in the Euclidean case, if no matter what kind of bounded domain you have, in the exterior case, if you make boundary parameter negative, you always have discrete spectrum. But in the hyperbolic case, you need to push boundary parameter a bit below 0 to create eigenvalues. And hyperbolic case is even more complicated than that, because if your domain is not convex, then this critical coupling parameter can be even positive. So even for positive boundary parameters, you can have eigenvalues below the bottom of the essential spectrum. And how to see that? We don't provide a proof in our paper, but heuristically, what one can, let's say, see that if this is your omega, and it is not simply connected, but we will make it simply connected, and this is omega x. It is let's say you take an annulus in the hyperbolic plane, so then the essential spectrum starts, and you impose, say, Neumann boundary condition on the boundary. The essential spectrum on such disconnected exterior domain is still 1 from 1,4 to infinity, but this operator on the bounded domain, it has eigenvalue 0. So if we make a small interconnection, then this eigenvalue moves up, but it still remains below the bottom of the essential spectrum. And even if we add some positive Robin parameter, this eigenvalue will still remain below the bottom of the essential spectrum. In some sense, in hyperbolic case, it is even interesting to study discrete spectrum of Neumann Laplacian on exterior domain, not only Robin Laplacian, because even Neumann Laplacian on exterior domain can have discrete spectrum in the hyperbolic case, which is different from. So we wanted to look at optimization of the lowest eigenvalue on exterior domain in the hyperbolic plane, and the candidate for optimal domain is exterior of the geodesic disk. So I introduce notation D for geodesic disk in the hyperbolic plane, and for geodesic disk we could estimate beta, the critical coupling constant at which the discrete eigenvalues appear, and by separation of variables we have found explicit expression for the ground state eigenfunction in terms of Legendre function of the second kind, and the order is given by this expression. So what is important for us is that this ground state is radial in geodesic polar coordinates, and actually we will use some properties of this function in our analysis, because it's not sufficient for us just to know that it's a radial function. In particular, we observed that if you are on exterior of geodesic disks, no matter what radius your disk have, you need to push the boundary parameter much sufficiently below 0 to create a discrete spectrum. And if your disk becomes very small, to create discrete spectrum, you need to push boundary parameter to minus, eventually to minus infinity to create discrete spectrum. So for exteriors of geodesic disks, we also have checked that the lowest eigenvalue is a non-increasing function of the radius. So if your disk radius is increasing, eigenvalue essentially goes down, and the critical boundary parameter is non-decreasing. So it is analogous to similar properties in the Euclidean case. And now I will pass to our results on optimization of the lowest Robin eigenvalue in the hyperbolic setting. So our main result is certain comparison between lowest eigenvalues on a general exterior domain in the hyperbolic plane and exterior of the geodesic disk. So what we proved, the following result. So omega is open bounded geodesically convex domain in the hyperbolic plane, and dr is a geodesic disk of radius r in the hyperbolic plane. So we proved that if hyperbolic cotangent of the radius of the disk exceeds isn't smaller than the ratio in the numerator, we have area of omega plus 2 pi divided by perimeter of omega, then the lowest Robin eigenvalue on the exterior of omega doesn't exceed the lowest Robin eigenvalue on the exterior of the geodesic disk with radius r, and this is true for all boundary parameters. So if omega is smooth, then we can use Gauss-Bonnet theorem, and then this fraction can be transformed into the average of the geodesic curvature of the boundary of our domain. And in some sense, the assumption that we have says that this quantity is the geodesic curvature of the boundary of the disk. So we essentially assume that the geodesic curvature of the boundary of the disk that isn't smaller than the average geodesic curvature of the boundary of omega. And in the hyperbolic case, there is some special case because this fraction can be smaller than 1, and in this, but this hyperbolic cotangent cannot be smaller than 1. So in this case, the lowest, if this holds, then the lowest Robin eigenvalue is smaller than any eigenvalue on the exterior of the disk for any radius. And our motivation for this comparison result was to prove some isoperimetric inequalities. And as a consequence of this comparison result, we proved the following. If omega is open, bounded, and geodesically convex set in the hyperbolic plane, and D is a geodesic disk in the same hyperbolic plane, such that either the area of omega is the same as the area of the disk, or the perimeter of omega is the same as the perimeter of the disk, then we have this inequality between the lowest Robin eigenvalues. And to verify this inequality, we used our main result. And if you denote by R star and R circle the radii of the disk such that either this holds or that holds, then for this radii you can verify that the condition that we have is satisfied, and it follows from geometric isoperimetric inequality in the hyperbolic plane. So let me say a few words about the arguments that we used in the proof of this result. So as you might expect, we used trial functions which depend on the distance to the boundary of the domain, and we introduced the distance function to the boundary of the exterior domain, and it's natural also to look at level curves of these distance functions, which are outer parallel curves, and I denote them by d omega t. And in hyperbolic case, in the exterior of a convex set, there is a formula for the length of this outer parallel curve, which is expressed through both perimeter and the area of your domain. And as trial functions, we used compositions of some smooth, compactly supported functions in the closure of the positive semi-axis with the distance function to the boundary of the hyperbolic plane, to distance to the boundary of the exterior domain in the hyperbolic plane. So by using these trial functions, we could estimate the lowest eigenvalue in the exterior of omega by infimum of all admissible psi's of the following Rayleigh quotient. Here we used the co-area formula, and then we substituted the length of the outer parallel curve in the hyperbolic plane, and we also divided this fraction by the perimeter. And then what we want to do is we want to replace this fraction by a larger number, which is in our assumption was hyperbolic cotangent of the radius. This is a bit tricky to do because in this case not only numerator increases, but also denominator increases. And if we would know that we eventually want to compare, if we would know that we want to compare with some negative eigenvalue, then we could do it, because this increases, but you can argue that most interesting psi's are those for which this is negative, and then this increases, and this also increases, but the whole fraction is negative, so the whole fraction increases. But in hyperbolic case, this eigenvalue can be also between 0 and 1/4. It can be positive, and to argue that this inequality holds, we had to have some additional argument. And to justify this, we have looked at, we have formulated the following claim and shown that it holds, that if you have some function phi, which is in a good Sobolev space, and it is positive, derivative is negative, and second derivative is positive, and it satisfies the Robin boundary condition at the origin, then we could check that this Rayleigh quotient as a function of S is increasing function just by computing the derivative of this Rayleigh quotient. Of course, for a fixed phi, and then we used expression of the ground state for exterior of the disk in terms of special functions to verify that this ground state as a function of distance to the boundary of the exterior of the disk satisfies these two assumptions, that it's decreasing and convex. Of course, this assumption is satisfied naturally. And finally, the missing step that we had in our proof, that this was the quantity we wanted to estimate. We can estimate from above by the same Rayleigh quotient, where we plug the ground state for the exterior of the disk. We can approximate this function by those psi's. And now we use this monotonicity claim that we had. So we can increase this parameter, which was parameter S, from this number to a larger number. So it becomes larger. And finally, this quantity is equal to what we wanted to estimate, because this is essentially the variational characterization of the lowest Robin eigenvalue in the exterior of the geodesic disk, and this should be attained on the ground state for the exterior of the disk. And okay, so our results were in exterior domains, but what happens in bounded domains? And maybe if I have still some time. So what we proved with Magda Khalil in 2022, that if omega is a bounded smooth simply connected domain in two-dimensional manifold with non-positive Gaussian curvature, and D is a Euclidean disk, then we could show that the lowest Robin eigenvalue for all negative boundary parameters on the bounded domain omega doesn't exceed this eigenvalue for the Euclidean disk. But then there was 1 month after our preprint appeared another preprint by Chinese mathematician Chen and Li, and they proved essentially is the parametric inequality for bounded domains in the hyperbolic plane. So they assume that omega is bounded smooth horoconvex domain. Horoconvex means that the geodesic curvature of the boundary isn't smaller than 1, and D is a geodesic disk of the same perimeter, and they could show that the lowest Robin eigenvalue for omega doesn't exceed that for the geodesic disk for negative boundary parameters. And we have sent our paper to them, and actually in our paper we had some kind of open question: what happens in bounded domain case? We don't know. We expect that the geodesic disk is an optimizer, and after that they updated they preprint and said that they solved our conjecture. So which we didn't expect them to do, but so this was for us a surprise. And of course, in this bounded domain case, there are many additional assumptions, like domain is horoconvex, and of course, a natural question if the same result holds for all domains which are just simply connected or at least convex. So this is not known, and actually the result is not restricted to two-dimensional hyperbolic planes. It's also for higher dimensional hyperbolic planes. So I wanted to finish my talk by some discussion. So what we proved that the exterior of the geodesic disk in hyperbolic plane maximizes the lowest Robin eigenvalue of the Laplacian Riemann exteriors of geodesically convex bounded domains with fixed area of perimeter. And this result is, of course, analogous to what we had in the Euclidean case, but when we started to work on this problem, we were not fully sure that the exterior of the geodesic disk is an optimizer. And the reasons for that are the following. First, the essential spectrum starts from 1/4, and you may have either positive or negative eigenvalues. And for example, in the case of Robin Laplacian on the bounded domain, of course the transition appears at alpha equal to 0 on the bounded domain, but you have some two regimes where if boundary parameter is negative, disk is maximizer and then becomes minimizer. So we were not sure. And another thing that worried us that you have this non-criticality of the Neumann Laplacian. So you need really to make your boundary parameter sufficiently negative to create discrete spectrum. And this is the same effect which happens in Euclidean case in higher dimensions than 3, in dimensions 3 or higher. And in Euclidean case, in those dimensions, the exterior of the ball was not an optimizer. So in the beginning, we were not fully sure that it holds. So, and this was the last slide of my talk.
Thank you very much. Does anybody have questions or comments? Yes, Daniel.
Can you give us maybe some intuition about the Euclidean thing? Why is 3 dimensions different than 2?
Well, in 3 dimensions, for example, if you fix, you say that the area of the boundary is the same as the area of the disk, you can probably create very thin and long domain, say in 3 dimensions, and you can essentially push the spectrum to 0. And so the lowest eigenvalue, if it is very thin and long, the lowest eigenvalue of Robin Laplacian will converge to 0. And in 2 dimensions, such an example cannot exist because if you try the same example, it won't. The lowest urban eigenvalue won't converge to zero. This is one reason. Another reason is this large coupling asymptotics by Constantine work. This is eventually how we concluded that it cannot work because of the asymptotics of the lowest eigenvalue as alpha tends to minus infinity is alpha maximum of the new curvature plus of alpha, and in 3 dimensions you can construct examples where this maximum of the curvature is not so somehow this is the asymptotics of the lowest eigenvalue, and in 3 dimensions and higher you can construct examples where this coefficient for omega is higher than for the ball. Sorry, smaller because it's negative.
Yes, the
Can you show the slide where you have your result and Chen Li's result, please?
Yes,
Both. So, do you have a counterpart to the? Because they assume that it's convex, or convex and the same perimeter. Do you have the counterpart to the 2-dimensional case where you only assume the perimeter to be fixed, but you don't assume convexity? Because in that case, the result should hold. It holds for the Euclidean space.
Yes. So what is?
So you forget that what I'm saying is that in the Euclidean space, in the Euclidean plane,
Yes.
higher dimensions is a different matter, but in the Euclidean plane, fixing the perimeter
Yes.
is enough to ensure that the disk is the maximizer.
Yes.
But there they have both Horo convexity and the perimeter. So what I'm asking is if you can say something about when you only fix the perimeter, because in your
This was my question. Yes. So if you don't assume Horo convexity, but just that the domain is simply connected, or maybe not simply connected. But I mean, I can say why they assume Horo convexity, because they used proof by Doren-Bocour and Trombetti and others, and in that proof it was it was Euclidean proof and Euclidean result, but in that result it was kind of important that the inner parallel surfaces for convex domains are also convex, if I'm not saying something incorrect. And if you just have convex domain in hyperbolic plane, the inner parallel surfaces are not necessarily convex. But if domain is Horo-convex, then the inner parallel surfaces are convex, Horo-convex. Sorry. So this was the assumption.
Any other questions or comments?